This is part 12 of the series Right Triangles and Trigonometry, and we're going to start this part with a second example in finding the area of a triangle that's not a right triangle. So here we have an obtuse triangle, and in this case it presents a special consideration here. Now I'm going to show you two ways to do this, and the easiest way is simply to create a right triangle by drawing an altitude so that we can get the height of this triangle. We could draw an altitude in this direction, but that would create a bunch of issues because we don't have this angle and we don't have this angle. But since we have this angle, let's go ahead and draw in that altitude. Now here's the altitude, and this is the height of the triangle, and I've just extended the side out. And we've learned in the past that triangles can have altitudes outside of the triangle. When we were dealing with orthocenter and things of that nature, we often had altitudes outside the triangle. So here is going to be our height. So let's go ahead and label this our height. And in order to find this height, we need this angle. We could use this angle, and I'm going to explain that in a second, but we know that this angle and this angle are supplementary because they're a linear pair. So if this is 127, then this angle would have to be 53. And then this becomes fairly easy. We can use basic sine, cosine, and tangent functions to find the length of this side. Some old horse would give us that length. So sine of 53 equals old horse, h over 24. So 24 sine 53 equals h. Now we know the base, so the area of this triangle is 1/2 base times height, so this is the base, 13, and the height is this, 24 sine 53. And we would just put this in the calculator. So we'd have 1 divided by 2 times 13 times 24 sine 53. Enter. Let's just make sure that we're in, yes, we're in degree mode. So our answer is 124.6 approximately. Now there's another way to do this. Notice that these two angles are supplements of each other. And if we take a look at what sine actually is, the sine of an angle is the y value. If this was our angle, and let's just say that the length of this hypotenuse is 1. If we were looking at this y value and this x value, we would have some old horse. So sine of theta equals y over 1, some old horse. Therefore, sine theta equals y. And cosine theta would be x, but we're concerned with the y at this point. Well, if the y is sine theta, then look at this piece. If this is some angle again, and it's the same angle as this, theta, and we say these angles are congruent, and this is 1 again, then we have the same situation, some old horse. So whether we're talking about this angle or this angle, it really doesn't matter, because the sine of that angle is going to be the exact same thing. So let's go ahead and verify that. What we're saying then is that sine 53 because this is sine of this angle, that this should be the same as 53 degrees going this way. So let's look at the sine of 127. The sine of 127 is 0.798, and the sine of 53 is the exact same value. So because we were dealing with this y, we could have used the 127 and we didn't have to do the calculation for 53. But it's a lot clearer when we do that, so you can exercise your discretion at this point and use whichever one you wish. I just consider it an interesting artifact that the sine of supplementary angles have the same value. Let's move on to the next section. In this section, we're going to look at a couple of tools that are going to allow us to use trigonometric functions with triangles that aren't right triangles. Here we have triangle ABC, and it's not a right triangle. Now, traditionally, the arrangement that you're going to see is when you have a vertex, it's usually going to be labeled with an uppercase letter, and the side opposite is going to be lettered with a lowercase letter of the same letter. So this is angle B, side B, angle C, side C. And that's how we're going to refer to these sides from this point forward. Now, to analyze this triangle, to find out the measures of sides and angles, we can still use sine and cosine. First, we're going to look at something known as the law of sines. And this gives us a relationship between these angles and their opposite sides. And the law of sines is stated: the sine of A over side A equals the sine of B over side B, which equals the sine of C over side C. And based on the rules of proportions, we can manipulate this to look like this. So you can also say A over sine A equals B over sine B equals C over sine C. And I think it's important to see where this comes from, and so I'm going to look at a brief algebraic proof of this theorem, or at least part of the theorem, because I don't think it's necessary to describe every instance, but we're going to look at the primary elements of this theorem. So the first thing I'm going to do is I'm going to draw in an altitude from vertex B down to side AC. Now with this altitude, we can establish a relationship between this angle, this side, and this side. So let's start with angle C, and we can say that this side relates to this side and this angle by some old horse sine. So sine of angle C equals old horse. And now if I were to solve for H, multiply both sides by A, so multiply this side by A, multiply this side by A, these cancel out, and I have A sine C equals H. Now I'm going to do the same thing, only I'm going to use this angle, some old horse. Sine A equals old horse. H over C. Again, I'm going to solve for H, so I multiply by C, and we have C sine A equals H. These cancel out. Now, let's go ahead and compare these two. Since C sine A equals H and A sine C equals H, I can say C sine A equals A sine C. And now, just with a slight manipulation here, I can divide both sides by A, and I have C sine A over A equals sine C. And then if I divide both sides by C, I have sine A over A equals sine C over C. And you can see that this is part of this relationship. We'd be able to do the exact same thing if we drew an altitude this way, and we could establish a relationship between angle C and angle B, and this H value if we established it here. So that's a very rough, quick proof of the law of sines theorem. And we're going to use this extensively as we move forward. But now let's look at the second rule that's going to allow us to deal with triangles. This next one isn't quite so straightforward, but it's just as helpful in certain situations. Now this rule is called the law of cosines, and as you can see it's a little bit more complicated than the law of sines, and the proof is equally complicated, but it's not too terribly bad. What we're going to do is the same thing. We're using the exact same triangle, and we're going to draw in our altitude, but this time we're going to need some other information. We're going to have to label this side. So what I'm going to do is I'm going to label this piece X. And if this whole side is B and this is X, then this is going to be B minus X. And I'm going to use that in my proof of this theorem. So the first thing I'm going to do is I'm going to use this triangle, and I'm going to set up a situation with the Pythagorean theorem using A, X, and H. So A squared equals H squared plus X squared, and now I'm going to solve this for H squared. A squared minus X squared equals H squared. Now I'm going to do the same thing for this triangle, and I'm going to say C squared equals B minus X squared, that's this side, plus H squared, this side. So the sum of the squares of the legs equals the square of the hypotenuse. Now I'm going to solve this one for H, so C squared minus B minus X squared equals H squared. I just subtracted this from both sides. Now we have this expression equals H squared, and this expression equals H squared. So I'm going to set those equal to each other. A squared minus X squared equals C squared minus B minus X squared. And what I'm going to do with this is I'm going to go ahead and expand this binomial. So the expansion of this is this term squared, this times 2, so it's minus 2bx, and with this negative sign it's plus 2bx, and this squared, so it's minus x squared. The x squared terms cancel out. We have a squared equals c squared minus b squared plus 2bx. Now I have this x term to deal with, so I'm going to do that by setting up a relationship between this angle, this side, and this side. The relationship is cot a horse, cos a equals b minus x over a, cot a horse, multiplied by a, so we have a cos a equals b minus x. We're going to add x to both sides and subtract a cos a, and we get this. Now we can substitute this expression for this x. So here we have x replaced by this expression here. We're going to multiply through by 2b, so 2b times b is 2b squared. 2b times negative cos a is minus 2b cos a. And negative b squared plus 2b squared is just b squared. So we have a squared equals c squared plus b squared minus 2bc cos a, which is this piece up here. And the other pieces are solved similarly. So I know that was a little complicated, but let's go ahead and use these theorems in some practical problems.